Hi guys, so in this final video we're going to be getting the results. We're going to be getting CT₀, CP₀, and FM, which is basically the efficiency of the propeller using results in Workbench. So first let's go to Workbench, and under the component systems there's something called results here. You want you to drag it there and then just drag solutions to results, right click results and click edit and just wait for it to load. So when everything loaded, you can see if we click on the tick buttons here, you can see the image showing on the right hand side in view 1. In your background it should be blue, and for me it's white, so that's fine. But right now we're gonna just use function tool. You can do whatever you want to. You can do some cool visuals and get the wake flow to show, but for now we're gonna be simple and we're gonna just extract the values by going to function here. And for function we want the function to be our force, and the location should be the blade, as you can see, and the direction is the Y direction, and click calculate. So when the value has been loaded, we're gonna just Control C this and paste it onto the Excel. And we're gonna do the same thing for torque. We need the torque value as well. So we're gonna scroll down to torque, and still on the y-axis, and then Control C this and Control V. Now we're gonna need to get P, and P is just equals to the torque value multiplied by angular velocity. These values are constants. The radius at 0.127, angular velocity at 733.04, which is 7,000 RPM. This is just in rads per second. And the disk area is just pi r squared, and density is 1.225. For our CT₀, we're going to use this equation right here. So we're going to do equals thrust divided by bracket density multiplied by the area multiplied by another bracket, and then the angular velocity multiplied by r, and then square that and then close the bracket and click enter, and that's your CT₀. And for the CP₀, we're gonna do the same thing, use this equation. So this divided by density multiplied by disk area multiplied by the angular velocity multiplied by the radius, all to the cube, and then close the brackets and click enter. And finally, for our efficiency, or FOM, this is just a special case we call FOM. We don't call it efficiency because we don't have the inlet velocity. The inlet velocity is at 0, and that's why they're called CP₀ and CT₀ here, and that's completely fine. But if you have an inlet velocity, that basically means the propeller is moving upward, so it's the relative velocity would be, let's say, when you're going up, it's, let's say, 2 or 3 meters per second, and then you're gonna use a different equation. But for now, we're just gonna use this equation, and I want you guys to do this also for the twisted propeller and see which one is better, or which one has the highest efficiency. The value here should be between 0 and 1. So first, let's do CT. to the power of bracket 3 over 2. I don't know, try to the power of here, to the power of, yes. And then divide this, and make sure you put another set of brackets just in case. So as if I'm dividing this whole number by, I can write here the square root, or bracket square root 2, and multiply that by CP, and then close the bracket. Click enter. And that's your FOM, or that's your efficiency. It's only basically 9% efficient. So the usual propeller is from 40 to 60%, or 0.4 to 0.6. So this is a really bad propeller. If you do the what's it called? The twisted propeller, it should give you a value between 0.4 to 0.6. So thank you guys for this propeller videos, and hopefully you guys have learned something. And yeah.